Hello everyone. Today I'm going to introduce our work, Lifelong Multi-Agent Pathfinding in Large-Scale Warehouses. Nowadays, in autonomous warehouse, hundreds of mobile robots are navigating autonomously to move inventory pods or packages from one location to another. The left video shows an Amazon Fulfillment Center. When you order an item on Amazon.com, a robot here will move to an inventory pod that contains the item you ordered, lift the pod, move the pod to a working station, and the human worker there will pick up the item and put it into the package. Once all packages are ready, they will be transformed to a sorting center. The sorting center will then sort the packages according to their destinations. So here, the yellow structure shows chutes. Each chute corresponds to a particular destination. And a human worker will first put one package on a robot, and the robot will then scan the barcode on the package, know its destination, and then deliver the package to the corresponding chute and drop it into it. In both centers, we need to address the navigation problem for a great number of robots. On the one hand, we want the robots to move as fast as possible, but on the other hand, we don't want them to collide with each other. A simple and traditional solution to this navigation problem is to use a single-agent pathfinding solver, where we plan a shortest path for each robot and resolve collisions between them on the fly. For example, if two robots are going to collide with each other, we can simply slow down one of the robots or ask one of the robots to take a detour. This method works pretty good for small-scale problems. However, when there are many chutes or many pods on the floor, or where there are many robots navigating in the warehouse, this could lead to heavy traffic congestion, just like the left video shows. Robots are waiting in lines and doing nothing, and this could generate very low throughput. Therefore, for the large-scale problems, we are interested in using multi-agent pathfinding solver to solve the problem. Where in a multi-agent pathfinding solver, the solver will consider all agents and plan passes for them jointly. It will generate collision-free passes with small travel time. And you can see from the video, under the same condition, the multi-agent pathfinding solver can generate solutions with almost no traffic congestion. So in this talk, I will first talk about multi-agent pathfinding, or for short MAPF, and its lifelong variant. I will then introduce three existing methods. Then I will talk about our new methods and compare it with the existing methods. Last, I will show some experimental results. First, MAPF. In this problem, we are given a graph and a team of agents, each with a start and a goal location. We assume that the time is discretized, and at each time step, an agent can either move to a neighboring location or wait at its current location. And we want to find a set of collision-free passes, one for each agent, while minimizing the sum of their travel times. Although MAPF is NP hard to solve optimally, in the past decade, people have invented dozens of algorithms to solve this problem. However, the MAPF problem is actually only a one-shot variant of the actual problem in warehouses. Because typically in a warehouse, after an agent reaches its goal location, it does not stop there and wait forever. Instead, it is assigned a new goal location and is required to keep moving. Therefore, the problem we are really interested in is lifelong MAPF, where agents are constantly assigned new goal locations. But the question is that how can we solve this lifelong MAPF? People have invented three methods to solve this problem. So the first method is to solve lifelong MAPF as a whole. This work formulates lifelong MAPF as an on-site programming problem, and thus can solve it optimally or suboptimally with completeness guarantee. However, these methods need to know all goal locations in advance, which might not be true in many real-world applications. And this method has very limited scalability. For example, in their paper, they only solve instance up to 20 agents and each with only about 4 goal locations. The second method is to decompose the lifelong MAPF into a sequence of MAPF instances. So at every time step, it solves a MAPF instance for all agents, where the start locations are the current locations of the agents, and the goal locations are the next goal locations of the agents. So this method can be applied in an online setting, so it does not need to know all goal locations in advance. And this method works faster than the previous method. However, this method needs to replan passes at every time step, or at least at those time steps when some agents have reached their goal locations, which may not be very practical in real-world applications. And also, this method might do a lot of repeated or redundant work. This is because every time when you replan a pass for an agent, you will discard their previous pass. And although you can use some incremental technique to save some such effort, you cannot avoid all repeated or redundant work. The third method overcomes the drawback of the second method by planning passes only for a subset of agents. It assumes that once a pass is assigned to an agent, the agent will commit to that pass. So it will never change the pass. As a result, the method only needs to plan passes for agents with new goal locations. So this method works pretty fast, but it still has some drawbacks. So first, because it only plans passes for a very small subset of agents, it cannot coordinate all agents very well. So sometimes it could generate poor quality solutions. And even worse, sometimes it might fail to find any solutions for the subset of agents. Therefore, this method can only work for a special class of maps called wareform maps, and thus it cannot be applied in all warehouse applications. Now let's look at our method. So we also want to decompose the lifelong MAPF into a sequence of MAPF instances. But instead of using standard MAPF instance, we solve a windowed MAPF instance for all agents with each time steps. So the windowed MAPF instance is different from MAPF instance in these following two ways. So the first one is that we only resolve collisions for the first W time steps. But of course, W should be at least as large as the replanning frequency H. And second, an agent in the windowed MAPF instance might be assigned a sequence of goal locations. And this is because we want to keep the agent busy in the next H time steps. So we don't want it to finish all its goal locations within H time steps. Many existing MAPF solvers can be easily adapted to solve windowed MAPF. In the paper, we show 4 examples: CBS, ECBS, CA*, and PBS. So for the first change, where we want to resolve collisions only for the first W time steps, for CBS and ECBS, we only need to change the collision detection function so that we only find collisions for the first W time steps and ignoring future collisions. For CA*, we need to change the low-level solver when we plan passes. So CA* plan passes by assuming that agent will not collide with any high-priority agents. So this time, we only consider the passes of high-priority agents only for the first W time steps. And note that this change with CA* is identical to an existing algorithm called WHC*, which is designed for standard MAPF. And last, for PBS. So PBS is basically a combination of CA* and CBS, and as a result, we need to change both its conflict detection function and its conflict avoidance function. This is for the first change. For the second one, there's an algorithm called multi-label A*, which can plan a single path for an agent that travels multiple goal locations. And we can use this multi-label A* to replace A* in the low level of these 4 algorithms. And then we can have the windowed MAPF solvers. So there are some advantages of our method. First of all, it works for all kinds of maps. And second, the user can design the replanning frequency according to their need. And third, because we only resolve collisions within a limited window, the solvers run significantly faster than the previous than the solver when you resolve collisions for the entire time horizon. And last, we could still produce high-quality solutions. And this is because resolving all collisions within the entire time horizon is often unnecessary since the paths of the agents can change as the new goal locations arrive. Imagine that we are in a very dynamic environment. So resolving a collision in a distinct future is unnecessary since your paths might change in the future anyway because of other agents. Now let's look at the experiments. We first test our algorithms in a fulfillment center. And we pick a map that is well-formed so that the method 3 can be applied here. So holding endpoints and dumping paths are two realizations of method 3, and we compare it with our method. When we look at the throughput, we can find that our methods produce the highest throughput. It improves the throughput by up to 7%. However, when you look at the runtime, our methods runs much slower than method 3. Therefore, so if you have a limited runtime budget, you might choose method 3 for this map. But if you prefer a higher throughput and have enough runtime budget, then you might choose our method. We also tested our algorithms in a sorting center. The map here is not well formed, and therefore method 3 cannot be applied here. We compare our results with different W, so different lengths of time horizons. The method 2, where we replan paths for all agents at every time step, is similar to our methods with W equal to infinity. If you look at every column in this table, so when you increase the W, the throughput doesn't change much. So it changes by at most 2%. But if you look at the runtime, a small W could reduce the runtime a lot, and as a result, have a higher scalability. So for example, here, we can serve up to 1,000 agents for W equal to 5 or 10. But when W equals to infinity, we can only serve up to 700 agents. And the results for the other 3 algorithms are similar. To summarize, in this work, we studied the lifelong MAPF problem. We introduced a new method that solves a windowed MAPF instance for all agents every H time steps. And there are many benefits of our method. It works for all kinds of maps. The users can decide the replanning frequency. It could produce high-quality solutions with small runtimes. And in experiments, we show that it can scale up to 1,000 agents in the simulated sorting centers. That's all for this talk. Thank you for listening.